3. This first section is we're going to do 3.1, which is a review and preview. Then in 3.2 we are going to talk about measures of center, and in 3.3 we're going to talk about measures of variability. Remember from chapter 1, when we talk about characteristics of a population, those numbers are called parameters. When we're talking about characteristics of a sample, those numbers are called statistics. And we talked about appropriate sampling methods, and most of the time a simple random sample is going to be your best sampling method. All of the statistic calculations that we're going to talk about really are only appropriate for simple random samples. Now in chapter 2 we talked mostly about the shape. So what we're going to do today is we're going to put numbers with center and we're going to put numbers with spread. Now we are going to look at mean, median, standard deviation, and variance in this section. In the next section we will talk about other important statistics in ways we describe sets of data. And so it's very important that you understand and interpret these important statistics. Now what we're doing is we are doing descriptive statistics in this chapter. That means we are simply summarizing or describing the important characteristics of our data sets. What we'll be doing in the second half of the course is we will be using inferential statistics, which means we are going to use our numbers to help us make generalizations about a population. We're going to use our numbers to help us make decisions. So the first thing we're going to talk about are measures of center. Now, there are different measures of center, some of which you have used quite often in your life and others you have not. There will be some that are mentioned in your textbook that we are not going to talk about. So we are going to look for that typical member of the data set. In your book they use the examples of chocolate chip cookies. And one of the things that must be done when we are doing this is we have to accurately define what our variable is. So the first thing we're going to talk about is we're going to talk about the arithmetic mean. And the arithmetic mean is the average that you have used most of your life. Now, in statistics, an average means any measure of center. So we need to use more specific language, and when we are going to add up our members of our data, their values, and divide by the number in the set, that's called a mean. And it's important that you use the right vocabulary in the right context. Here we have a comic strip that kind of talks about the difference between average and mean, and I will leave you to read that yourself. Now we have some important data, and we will look at this first symbol, which looks like a real fancy capital E, is a capital Greek letter sigma. And when you see that in front of something, that means you add up whatever follows. So sigma means sum of. We're going to talk about x as our variable. Sometimes we will put a subscript of I behind it, meaning individual x. A lowercase n represents the number of data values we have in the sample, and a capital N represents the number of data values we have in the population. When we talk about mean, we're going to use the symbol, an X with a bar over it. And we usually say X bar, or I will say mean. And X bar is the sum of all the individual X's divided by the number in the sample. When we are talking about the mean of a population, we use the lowercase Greek letter mu which looks a little bit like a U, we use that to mean mean. And it means we're going to add up all the individuals in the population and divide by the number in the population. One of the things that we look at, and one of the things we try to do in statistics, when you use the regular alphabet, that stands for a statistic. When you use the Greek alphabet, that stands for a parameter. So both of these stand for mean. X bar is the mean of a sample, so it's a statistic. Mu is the mean of a population, so it's a parameter. Now, the mean is reliable, and when we look at samples, the mean does not vary as much as some of the other measures of center, and this is because it takes every data value into account. One of the disadvantages is the same as its advantage, is that it's sensitive to every data value. So one extreme value can affect it dramatically. In statistics, this is called resistance. So the mean is not a resistant measure, meaning that extreme values can...
So let's just look at an example of how the mean can be affected by outliers. Let's say I have 4 children in the room. I have a 3-year-old, a 4-year-old, a 5-year-old, and an 8-year-old. I want to find the mean of this data set. So this will be set A. So the mean of set A will be 3 plus 4 is 7 plus 5 is 12 plus 8 is 20 divided by 4. So the mean age is 5 years. Now let's say that in set B I have these same 4 children. And I have a 10-year-old come in. No, I don't want to do 10-year-old. I want to do, well, yeah, we can do 10-year-old. Okay? So the mean of B is going to be 30 divided by 5, which is 6 years. So this older child comes in, is quite a bit older than the first 3, and does raise our mean age. But let's say the 10-year-old goes away, and we have a 30-year-old come in. So now the mean of set C is going to be, I don't think I did this very well, 10 plus 30 is 50 divided by 5. So my mean age for those 5 children went up 10 years. So notice that the difference between set A and C is only that 30-year-old, but that 30-year-old coming into the room raised our mean by 5 years. So this is what it means to be a non-resistant measure.
Now the median is the middle value. When you put your data values in order, then the median is the middle value. Your book uses X tilde, a squiggle line above the X, to stand for median, but in a lot of textbooks it's denoted by a capital M. The good thing about the median that it's not as affected by extreme values, so it is a resistant measure of center. So what's true about the median is half of the ordered values are less than or equal to the median, and half of the ordered values are greater than or equal to the median. So again, the big difference about median is you must put your data values in order. If the number of data values is odd, your median will be a member of your data set. If your number of values is even, the median will be the average of the two middle ordered values, which may or may not be a member of the data set. So the first thing we do is we sort the values. Then again, if the data values, number of values is odd, the median will be in the middle. If it's even, the data value will be the mean of the two middle numbers. So you find the two middle numbers, add them up, divide by 2. Here is an example of a formula, but it's L of M, L meaning location. So this tells you how you find the location of the median in your data set after it has been put in order. So you take the number of the data values plus 1 divide by 2, and that gives you the location of the median. So for instance, if I had 25 data values, 25 plus 1 is 26 divided by 2. So the 13th value from the top or the 13th value from the bottom will be your median. So here's an example of a data set, and you'll notice they're not in order. So the first thing I must do is put them in order. Now I have 6 pieces of data. So I'm going to do 6 plus 1 is 7. 7 divided by 2 is 3.5. So my median is going to be halfway between the two middle values. So what I'm going to do is I'm going to add those up, which I'll get 1.83, and then I'm going to divide by 2. And that will give me my median, which is 0.915. So now I have a second set of data, and you can see from this one I have 7 individuals in my data set. So I'm going to do 7 plus 1 divided by 2, which is 7 plus 1 is 8. Divided by 2 is 4. So once they're in order, it's going to be the 4th data value. So my median is going to be 1, 2, 3, 4 from the bottom, or 1, 2, 3, 4 from the top. It doesn't matter that we have 2 that are exactly the same. So in this one, the median is 0.73. It is a member of our set. Now the mode is the value that occurs with the greatest frequency. The data set can have one or more than one or no mode. What happens with the mode is it really isn't very useful, so we don't use it very often. Your data set can be bimodal, meaning that it has 2 values that occur with the same frequency. It can be multimodal, that a whole bunch of values occur with the same frequency, or it could have no mode in that no data value is repeated. The mode is the only measure of central tendency that can be used with nominal data. So if we were looking for eye color, or we were looking at our M&Ms, the color that happened most often is the mode, and that's really the only measure of central tendency that we can use. For example, in set A, you can see that, and in looking at that, I see that 1.10 happens twice, so that's the mode. Notice that in data set B, 27 happens 3 times, 55 happens 3 times, so it's bimodal, it has 2 modes. And notice in set C that no number happens more often than any others, so we say it has no mode. Now the mid-range is halfway between the maximum and minimum values, and I will tell you that you don't use that very often at all. So sometimes it's kind of nice to know where it is, but because it only uses the maximum and minimum values, it is very rarely used. So we take the maximum value, add it to the minimum value, divide by 2. It is very sensitive to extremes, but it is very easy to compute. It reinforces that there are several ways to define the center, and this does avoid confusion with the median because now we're looking at the distance from the mid-range to the maximum is the same as the distance from the mid-range to the minimum. Where remember with the median, you had the same number of data values above and below the median. Data values, not distance. Okay. We are going to put in a slide here for round-off rules because now that we're doing calculations, that's going to be important to you. And I will tell you, most of the time, our round-off rule is carry it one more decimal place than is present in the original set of values. So if your data set is rounded to the nearest 1, you will round your calculated value to the nearest 10th. If your data set is rounded to the nearest 10th, you will round your calculated value to the nearest 100th. So when we find the measures of center, we want to think whether the results are reasonable or not. Let's think about the method used to collect the sample data, because that really does tell us what measure of center is most appropriate. Now, what do we do first? When we want to talk about the mean, we find the sum of all the values, divide by the number there are. It's sensitive, and sample means tend to vary less than other measures. When the mean doesn't make sense for some reason, or the data is very skewed, then we may use the median, because then that tells us the number of data values above and below the median is the same. For instance, if you're going to buy a new house in a new community, the data that the Chamber of Commerce reports is the median value, meaning that half the houses in the community cost more than that value, half the houses cost less than that value. The mode is sometimes useful. It's the one that occurs most frequently. It really is good when you're using nominal data. And then there's the mid-range. That's easy to compute but very rarely used because it doesn't give us a whole lot of information. Now let's talk about the shape of the data, which we talked about in Chapter 2, but remember, we have symmetric distributions if we can fold it in half and both halves are roughly the same. We have skewed when they're not symmetric. So remember, this one where the tail extends to the left is left skewed. This one that the tail extends to the right is right skewed. Skewed to the left is also called negatively skewed, and skewed to the right is also called positively skewed. The mean and the median are in different places in different types of distributions, but it is not always sure. It gives us hints. So when we have a symmetric distribution, the mean and the median should be close together. In fact, when we have a very symmetrical distribution, the mean and the median are the same. In a skewed distribution, because the mean is not as resistant and is affected by outliers, the mean is pulled in the direction of the extreme value. So, comparing the mean and the median. the mean is very influenced by outliers. The median is resistant, less influenced. We use the median when typical is needed, half above, half below. We use mean when the total is important. So for instance, the Chamber of Commerce will report the median housing price, but the tax assessor talks about the mean housing cost, because to the tax assessor the total value of all the homes in the city or county are very important, because the assessor wants to take the mean times the number of houses and get a value. And so both the mean and the median are measures of the middle, but they are useful in different ways. Now, when we look at skewedness, remember in a symmetric distribution, the mean and the median are in the same place, and the mode. When we have a skewed distribution, the mean is pulled, so the mean will be less than the median. The mode is always where the peak is, so the mode really doesn't give us too many clues. Other than when both the mean and the median are less than the mode, it gives you a clue that we have a negatively skewed distribution. When we have a positively skewed distribution, the mean is pulled further out in the tail. Now the median is going to be where we could balance this distribution. So if we cut this distribution out of foam core board and we tried to balance it, the place it's going to balance is at the median, because you basically have half of the distribution above and half of the distribution below. So we have talked about measures of center, so we've talked extensively about mean, median, and mode. What we're going to talk about next is the measures of variation, and we are going to talk about understanding and interpreting them. There is an equation that's associated with standard deviation. I'm going to show you how to calculate it by hand with a very small data set, and I'm going to show you how to calculate it on StatCrunch. I am going to ask that you do it once by hand, and then I'm also going to ask that most of the time you're going to use StatCrunch because it just takes less time. There's fewer places to make a mistake. But it's important that you do at least one hand calculation so you understand the formula. So now when we talk about measures of variation, the easiest one to calculate is the range. And the range is simply the difference between the maximum and the minimum values. It's just the distance between those two. It's very sensitive to extreme values. It's not as useful as other measures of variation, but there it is. So the range and the midpoint kind of go together. They're easy to calculate, but we don't use them very often. Again, we're going to carry our calculated value one more decimal place than the original set of data. When you're doing a series of calculations by hand, it's very important that you do not round in the middle of your calculation. Very important. So let's do the standard deviation. The standard deviation for a sample is denoted by a lowercase s. So this tells us the average distance of the data points from the mean. So when we get done calculating a standard deviation, it really does talk to us about how the data vary. On average, the points are this value from the mean. If the standard deviation is small, we know that the data are clustered close to the mean. If the standard deviation is relatively large, then we know the data are quite spread out. Here is the formula. Now, order of operations is very, very important. So remember, we're going to go to the innermost calculation first. So the first thing you do is you take each individual score and subtract it from the mean. Once you do that for all your data points, then you're going to square each data point. Once you square them, then you add those all up. You're going to divide that sum by the number in the sample minus 1. And lastly, you're going to take the square root of that calculation. Now, one of the things that happens is we talk about these are measures of variation, and one of the measures of variation is variance. Variance is simply the square of the standard deviation. So variance is going to be s squared, and then we just would not take the square root of that. We do not use variance very often because it's very hard to interpret. The variation is much easier to interpret. Here is the Archaeopteryx data, and we will look at this and do a hand calculation of the standard deviation of the femur, and then we are going to do the calculation of the standard deviation, both the femur and the humerus, in StatCrunch.
So we are going to do the Archaeopteryx standard deviation mean by hand, and I just want to show you, remember the formula for the mean is the sum of all the individual data divided by the number of the data. So if we look at the Archaeopteryx, we are going to, and I'm just going to do the femur, we're going to do 38 plus 56 plus 59 plus 64 plus 74, and we're going to add all those up and we're going to divide by 5. So that's going to be 291 divided by 5, which comes out to 58.2. Now remember, this does have units. That would be 58.2 centimeters. Remember, rule of thumb is to take your calculated number, your statistic, out one place value further than your original data. Our data was to the nearest 1, so we'll round our mean to the nearest tenth, and this does come out exactly even. So we know that the mean length of the Archaeopteryx femur is going to be 58.2 centimeters. Oops, I didn't mean to put it there. 58.2 centimeters. Now let's go ahead and do the standard deviation. Now remember, the formula for the standard deviation is that S, and we use a lowercase s to stand for the sample standard deviation, and it is going to be the sum of each individual value minus the mean, and then because some of those are positive and some of those are negative, we square it to get rid of the negatives. We're going to divide by n minus 1, and then we take the square root of the whole thing. So let's go ahead and let's set up a table, and I'm going to put my values for my femur. Let's go back up, femur. So I'm going to put my values here, 38, 56, 59, 64, And I'm going to set this up. So this is my x. Now I want to do my individual x minus the mean. Then I'm going to square it. And then I'll finish up. So I'm going to do 38 minus 58.2. I'm going to do 56 minus 58.2. I'm going to do 59 minus 58.2. 64 minus 58.2. And 74 minus 58.2. So now you can see I did those calculations. We have some negative numbers and we have some positive numbers. If you're going to be doing this by hand, you'll want to come up with the sum of this column, and it should always be 0. That's part of the reason why in the next step we have to square everything, because otherwise the number of 0 doesn't give us any information. So now I'm going to square those 5 differences. So now I've squared them, and by squaring them I've eliminated any negative signs. And do not round at this. We just take it as it is, and when I add this up, this comes out to be 696.80. Now, go back to my formula. The next thing I'm going to do is divide by n minus 1. So I'm going to take 696.80 divided by, I have 5 individuals minus 1. I'm going to divide it by 4. And when I do that, I get 174.2. And then I want to take the square root of everything. And I get 13.198, and it goes on and on and on. Now this is the place where I go back to my original data. It was ones, so I'm going to take it to the nearest tenth, so it would round to 13.2, and my units on my standard deviation is the same as the units of my data, so it'd be 13.2 centimeters. That's going to be the standard deviation of my femur for this Archaeopteryx. As you can see, doing it by hand is tedious, but it does give you a feel for the formula. So I would recommend you do a small data set or 2 by hand, because that's going to be important to help you understand the definition of standard deviation.
We're going to use StatCrunch to help us calculate the mean and the standard deviation for the Archaeopteryx data that is on slide 37 in the PowerPoint presentation. You can rename your variables just by going up to the top and typing over it. So I'm going to do my femur first, and then I'm going to do my humerus. Oops, I better spell it right. And then I'm simply going to type in my data. Okay, now when you're going to do your calculations, you go up to Stat. I want to start with summary statistics. That's where we find the mean and the standard deviation, and my data is in columns, and I want to select both columns. We might as well do it at the same time. So if you do shift click, you can choose more than one column, and I'm going to double check. It'll tell me the number, the mean, the variance, the standard deviation, the standard error, minimum, maximum, and the quartiles, and does it tell us the median? I was double checking for that. So that's everything we're ever going to need for this, so I'm going to do compute, and there they are. Femur, I have 5 and 5, tells me the mean, the variance. Remember, the standard deviation is the square root of the variance. What does the standard deviation tell me about this data? It says on average the femurs were closer to the mean than the humerus bones. And so on average that's going to be 15.9. On average the femur will be 13.2. And remember, we take our statistical numbers and we take them one place value more than our data. And so since our data was to the nearest 1, we're going to take the numbers that were in those. The standard deviation is a measure of the variance. So in other words, the standard deviation is also a non-resistant measure because you use the mean to calculate it. So since those extreme values affect the mean, they'll also affect the standard deviation. And standard deviation does have units, and the units are the same as the original units of the data set. When you have sample means that are approximately the same, then it's good to look and compare the standard deviations. We really aren't going to use standard deviations to judge the difference between samples. We basically use the standard deviations to describe our one set. When we use when we're going to compare the variation with different means, we're going to use the coefficient of variation, which we're going to talk about later. But the coefficient of variation is, and it is your standard deviation divided by the mean. And so you look at a percentage. What is the standard deviation compared to the mean, and you look at it as a percent. When you talk about the population standard deviation, the formula is similar. We're going to take our individual scores, we're going to minus the population mean. We're going to square that difference to get rid of any negative numbers, and we're going to add them up. And then we divide by the number in the population. The biggest difference between the population standard deviation and the sample standard deviation is in the population standard deviation, we don't subtract 1. Chances of you calculating this are slim to none. Now, the variance is equal to the square of the standard deviation. So the sample variance is the formula for sample standard deviation. We just don't take the square root of it. The population variance is the formula is the same as sigma, which is a lowercase Greek letter sigma. So this little thing that looks like a old-fashioned bomb with a fuse, that is a sigma. So sigma is standard deviation, sigma square is the variance. So again, you just don't take the square root of it to find the value for the variance. Now, what we're doing in statistics is we are trying to estimate the parameter using a statistic. And these calculations that we've talked about, we're looking at unbiased estimators. So we use the sample variance or the sample standard deviation to estimate the population variance or the population standard deviation. So what happens is when we use an unbiased estimator, they tend to target the value that we're interested in. A biased estimator would systematically over or underestimate the value that we're interested in. So when we talk about S, estimating sigma, sample standard deviation is an unbiased estimator of population standard deviation. So again, here we have S has to do with the sample, the standard deviation, and then squared is the sample variance. Sigma stands for the population standard deviation. Sigma squared is the population variance. Now range is, remember, was the top and the bottom. The difference between the top and the bottom. And we're going to talk about normal distributions in chapter 4 or 5. And chapter 5, I believe. And we're going to talk about this a little more. But when we talk about normal distributions, most of the individuals lie within 2 standard deviations of the mean. In fact, 95% of the individuals in a data set usually lie within 2 standard deviations of the mean. Now, usual. Usual means most of the time. And so we can use the range rule of thumb to give us rough estimates of usual, because as we go forward we're going to see, is our value that we got from our calculations, is it usual or unusual? And remember in class we talked about the difference between statistically significant and statistically insignificant. When things are statistically significant, they are unusual if the mean that we assumed was true is actually true. So the minimum usual value is going to be the mean minus 2 standard deviations. The maximum usual value will be the mean plus 2 standard deviation units. When you don't need to calculate the standard deviation, you can take the range and divide it by 4 and you will be in the right ballpark. So if we look at the range, the difference between the maximum and minimum values divided by 4, we will get a very rough estimate of the standard deviation. Good enough to decide what's usual and unusual. Okay, again, standard deviation measures the variation among the data values. When data values are close together, you'll have a very small standard deviation. But when the values but if the standard deviation is larger, you will have much more variation in the values. And again, standard deviation does have units, and it's the same units as the original data set. For many data sets, unusual means it is either 2 standard deviation units above the mean or 2 standard deviation units below the mean, and only compare standard deviations if they use the same scale in units and their means are approximately the same. Now, this is talking about the usual, unusual. So we're going to talk about an approximately bell-shaped curve, which we will call normal. And here is what is true about a normal distribution. In a normal distribution, 68% of all values fall within 1 standard deviation unit of the mean. That's more than 2/3. 95% of all values fall within 2 standard deviation units of the mean. Almost everybody. And almost everybody, 99.7% of all values fall within 3 standard deviation units of the mean. So here's a picture. So here's our mean in the middle. We go above the mean 1 standard deviation unit, below the mean 1 standard deviation unit, and we have 68% of the individuals in that data set will fall in that. For IQ is a test to measure intelligence, and IQ is designed to have a mean of 100 and a standard deviation of 15. So what this says is 68% of human beings in the United States have an IQ between 85 and 115. Okay. 95% of all individuals have an IQ of between 70 and 130. So that's 100 minus 2 standard deviations, 100 plus 2 standard deviations. And 99.7% of the individuals will have an IQ of between 55 and 145. And then there are those people who are above 145, those people who are below 55. Does that make sense? So I want you to think about that. I am going to put in some examples of that before I let you see this lecture. And here's an example. So this is what I was trying to think about before. So if we look at heights of adult men from ages 18 to 24, and I'm going to tell you that we use these ages because this is college age. And many studies are done on college age people, mainly because they're at the university, they're taking some kind of class, and it's easy to require them to be a subject in an experiment. So that's how we do get an awful lot of data. So this study was performed in the late 70s, and they found that the mean height of adult men 18 to 24 was 70 inches. The standard deviation was 2.8 inches. They did a graph of the data and found that it was bell-shaped and symmetrical. So that means it's a normal distribution. When we have a normal distribution, we use a capital N just to stand for normal. The first number is our mean, and the second number in the parentheses is our standard deviation. So we look at our empirical rule, which is also known as the 68-95-99.7 rule, and we know that 68% of men between 18 and 24 are between 67.2 inches and 72.8 inches. So we know they are between a little more than 5'7" to a little less than 6'1". 95% of the data of the young men will have heights between 64.4 and 75.6. So that's 2 standard deviation units. So that's 5.6 inches higher than the mean, 5.6 inches lower than the mean. So we know that 95% of men 18 to 24 are between 5'4.5" and 6'3.5" approximately. And we know that 99.7% are within 3 standard deviation units. So 3 times 2.8 is 8.4. And so we know that almost all young men between 18 and 24 are going to be between 5'1.5" and 6'6.5". Now you may know people who are young men who are shorter than 5'1" and taller than 6'6", but they're going to be in this 0.3%. And here we have it visual. So again, 68 between these two heights, 68%, 95% between 2 standard deviation units above and below, and 99.7% 2 standard deviation units, 3 standard deviation units above and below. Now, when we calculate standard deviation, why do we use n-1? And I'm going to tell you it just gives us better results. And so in other words, it helps our sample standard deviation be a better estimator of our population standard deviation. And so we will never underestimate our population standard deviation when we use that n-1 in our calculation for our sample standard deviation. And this is the coefficient of variation that we talked about earlier. So remember, if you have samples that have very different means and you want to compare their variation, the better way to do it is to use the coefficient of variation, which is your standard deviation divided by your mean times 100. So in other words, you're looking at what percent is the standard deviation of the value of the mean. So that way you can calculate those percents from population to population, and those are comparable. So what have we done in this section? We've looked at range, we've looked at the standard deviation of a sample and a population, we've looked at variance of a sample and population, and we used the range rule of thumb. We talked about the empirical rule. Sometimes it's called the 68-95-99.7 rule, and we've talked about the coefficient of variation. So that is what we are going to look at. That's what we have looked at in this section. I would stop here and do your 3.2, 3.3 homework.